Hey, Jonathan here at Colfax Math. Today I'm going to go over the top 20 big ideas in an Algebra 2 or Integrated 3 math class. So that would be the second year of high school algebra. There's more ideas than that, but I'm going to go over the top 20. It's just a really quick recap just to make sure you understand what the words and vocabulary are.
Measure the height. Measure the width from here to here.
Laminated overnight on a CNC
Next
cut
Thursday,
jig.
we have 20 ELOs. Where we started the whole class in Integrated 3 is really with domain and range. Domain is the possible values of x, and range is the possible values of y. And usually it's a reference to the Cartesian coordinate plane. Horizontal axis is always x, vertical axis is always y. If I want to regulate my graph on the x-axis by cutting it off, it would be a domain. I'd cut it off, say, between -2 and 4. Or if I want to regulate on the y-axis, I would use a range and cut it off, say, between 0 and 5. So that's ELO number 1. Usually that domain is going to be written, x is greater than 0 and less than 10, something like that with inequalities. ELO number 2 is function notation. Function notation is usually saying f of x, and f of x is replacing y. Again, on a Cartesian coordinate plane, the definition of a function is that there's only one corresponding y value for any given x value. So the way you could tell whether it's a function is with the vertical line test. So if I have a graph like this, and I draw a vertical line anywhere on there, and it only crosses it in one place, then yes, it is a function, because there's only one y value for any given x. But if the graph instead looked like this, and I drew a vertical line, I could see at a given x value there are 2 y values, so no, it is not a function. So that's what a function is. A lot of times if I have f of x is equal to 3x plus 5, a linear function like that, and I'm asking you to find, say, f of 2. F of 2 is saying take 2, plug it in for x, to get 3 times x plus 5, or f of 2 is equal to 11. So that's given an independent variable, solve for your dependent variable y, but the reverse you could also do. So if f of x is equal to 10, solve for x. Here I would take that 10 and plug it in for f of x. Now I'd have to solve for x, isolating the variable x. I would subtract 5 from both sides to get 5 is equal to 3x. Still solving for x, I divide both sides by 3. So when f of x is equal to 10, x is equal to 5/3. That's pretty much function notation. ELO number 3 goes to factoring. And this is actually a really big idea on factoring, the difference between an expression and an equation. So if I have 3x squared plus 6x, that's an expression because there's no equal sign on it. And the best thing to do there is just factor out the common term. So I'd pull out a 3x, leaving me with an x and a 2. The reverse of factoring is distribution, so the check is multiplying that through to get 3x squared plus 6x. Are we good to go there? The other way I could factor, so again, this is an expression. If it's set equal to 0, then I could use the zero-sum property to solve. But only when it's an equation. If it's an expression, I can't solve for x because there's no equal sign. So if it's an equation like this, I do the exact same thing. I factor out the common term of 3x, leaving me with x and 2. Now number 5, our zero-sum property, is once we factor, we have things multiplied together to equal 0. That means either this has to equal 0 or this has to equal 0. Zero-sum property. So that means either the 3x is equal to 0 or x plus 2 is equal to 0. Divide both sides by 3, x is equal to 0 or x x is equal to -2. So first we have factoring, and then from factoring, we have the zero-sum property in an equation to solve for 0. Okay, number 5 is exponents. So number 5 is exponents. The rules of exponents are x to the m to the power of n. Here I multiply, get x to the mn. X to the m times x to the n is equal to x m plus n. Anything to the 0 power is equal to 1. Division x to the m divided by x to the n. Here I subtract exponents. And then square root x to the n to the mth root. This is always my numerator right here. This is x to the n divided by m. You do have to know those exponents. They really come in a lot. So those are rules of exponents. An example would be, if I have 5x to the 5th, y quantity squared times z to the 3rd divided by x squared or something like that, or z. First order of operations is I distribute using this rule of exponents here, that 2 through the quantity to get 5x to the 10th, y squared z to the 3rd, all over x squared z to the 1st. Now I'm going to use this rule of exponents here. The 5 stays in the numerator. 10 minus 2 is 8. Y is by itself, so I still have y squared. And then 3 minus 1 is 2. So that's how I simplify. Again, that's an expression. Rules of exponents. All right, still carrying on. We've kind of gone 1 through 5. Working with exponents. Rules of exponents are really important. Let's move on to our number 6 big idea, box plots. Let's say I have a set of data, ages of students in class, 14, 15, 16, 16, 17. That's good. So I have 5 ages in class here. And again, this is box plots. First thing I want to do is find the median. That's the middle value. So the middle value right here would be 16. It's an odd number of values, so it's going to be the middle one with the same amount on both sides. If it were an even number of values instead, I would take the 2 middle ones, 16 and 16, and average those two. Okay, so the average of 16 and 16 is 16, and that's the median, the middle value. And then I need to find the first quartile. So of this median at 16, there are 3 values below it, 3 values above it. So the first quartile would be halfway in the first half of values, or 15. And the second half of values is 3, and it would be the middle value, 17. So I have my median, my first quartile, my third quartile. The interquartile range is the third quartile minus the first quartile, or 2. The overall range is the largest value minus the smallest value, 4. The median is the middle value. The mode is the one that happens most frequently. So in this set of data, it would be 16. And the mean, or the average, is I add up all the values and divide by the number of values. To graph this box plot, I put a scale down, and I could label it from in values of 2, say, so I go 10, 12, 14, 16, 18. The median's right here at 16. The first quartile goes down to 15. The third quartile is 17. That's my box. So that covers half of my values. And then the fourth quartile goes from 17 up to 18. So that's a quarter of the values. Second quarter of the values, third quarter of the values, and then the first quarter of values. So that's a box plot. 7 equations of a parabola. I'll write in pen equations of a parabola. This is given a picture. Find the equation. So a parabola is always going to be in the form y equals x squared. Something like this. It's a parabola opening up. It's a conic section. The general equation of a parabola is y equals a x minus h, quantity squared, plus k, with a vertex at the coordinate hk and a dilation of a. So if I have these points in my picture, let's say over 3 up a negative 1, and another point on here like this, let's say that point over here is negative 1, 4, and I want to take that picture and put it in my vertex form. I would say y is equal to a x minus h. H is a horizontal component, the x part. So x minus 3, quantity squared, plus k, and k is negative 1. I still need to solve for my a value. I have a coordinate on my graph, negative 1, 4. That's a coordinate, negative 1, 4. It's an xy value. I'm going to take that negative 1 and plug it in here for x. Take that 4, plug it in here for y, and solve for a. So I have 4 is equal to a, negative 1 minus 3 squared minus 1. 4 is equal to a, negative 1 minus 3, negative 4 squared is 16, minus 1. I'm going to add 1 to both sides to get a times 16. Adding 1 to both sides gives me 5. Divide both sides by 16, and a is equal to 5/16. So now I have my value for a, my dilation value. For my general equation, I go to my specific equation, y equals 5/16, x minus h, quantity squared, plus k, or plus a negative 1. So that's number 7, finding the equation of a parabola from a graph. This is really a very big idea in math, and Algebra 2 is the ability to go from pictures to equations, from equations to pictures, from scenarios or data sets, be able to graph it and then find the equation of it. It's really how you build models, and model building is kind of the foundation of science. And then you have to decode the word problem into a picture, and then from that picture you follow the exact same scenario in finding the specific equation. Number 9 is given a quadratic and turn it into the graphing form of a parabola. So let's say we have y equals x squared minus 2x minus 3. So this is a quadratic, remembering that a quadratic is y equals ax squared plus bx plus c. I could solve that quadratic by setting it equal to 0 and then factoring to solve for x, and then use the zero sum property that we talked about earlier. Or if I can't factor it, which we talked about earlier, then I could use a quadratic equation. But that's not what we're doing here. Number 9 on my list is turn this into vertex form. So I like a general roadmap first, so I'm going to make that y equals a x minus h, quantity squared, plus k. Okay, so again, this is a general form of a parabola. If I have the general form first, I can manipulate this quadratic into that general form. The way I do that is I set that 3 off to the side, so I still keep it part of my equation. So I still have that negative 3, I'm just setting it off to the side there. And then this is called completing the square to get into the general form. The way I complete the square is I take half of this value and I square it. So half of negative 2, negative 1, squared is 1. I can't just add 1 onto the right side of an equation without knocking it out of value. So I have to add 1 to the left side, or, which is equivalent, subtract 1 from the right side. The whole reason I complete the square here is so I can get a perfect square. So now I have y equals x, half of that value, minus 1, quantity squared, minus 4. Now I'm in the general form, the vertex form of a parabola. My a value would be a 1. And what I did here again is complete the square to get into vertex form to get a perfect square. If I FOIL this thing out, it would give me x squared minus x minus 2x plus 1, and that's why I completed the square. All right, hopefully you're holding strong here. This is, again, not to teach you all the ideas in the Integrated 3 class or Algebra 2 class, but rather just to give you a quick review of all of the big ideas in Algebra 2, just a quick refresher. Number 11 is general parent graphs. So the first thing you need to know is kind of all the functions we looked at. We have linear, a straight line, y equals mx plus b. From linear we went to parabola, y equals x squared. These are all parent graphs. Then we went to a cubic function. A cubic is y equals x to the third. Then we had a hyperbola, or inverse. And the inverse is y equals 1 over x. And then we had a square root, y equals the square root of x, and absolute value, y equals the absolute value of x. So those are all of our parent graphs, and also be able to recognize what the graph looks like. This is a straight line. This is like a U shape, up or down or side to side. A cubic looks like that as a parent graph. Inverse, negative, it'll be third quadrant for when x is negative, y is negative, or first quadrant, x is positive, y is positive. Square root is increasing at a decreasing rate, because as x gets larger, y gets larger, but at a decreasing rate. Absolute value is a V shape. Right, so absolute value is a V shape. And one more, we have exponential. Exponential is y is equal to 2 to the x. And that graph actually is different in the square root because it increases at an increasing rate with the y-intercept greater than 0. So those are our parent graphs. And then from those parent graphs, we transform those parent graphs, meaning that we added an a value for dilation and a hk for moving the vertex around. And you should be able to do that with every one of those kinds of functions. So as an example of a cubic, right, as a cubic, we have y is now equal to a x minus h, quantity cubed plus k. This is a cubic function with a new vertex at hk, and then either it's kind of elongated or scrunched together based on a. And we could be able to find all those equations like we did with the parabola. All right, then number 12 is circles. And circles is pretty similar to all of these functions. The parent graph of a circle is x squared plus y squared equals radius squared. And I could do the same thing with that circle, transpose it by moving it around by going x minus h, quantity squared, plus y minus k, quantity squared equals r squared. So as an example of that circle, if I had x minus 2, quantity squared plus y plus 3 squared equals 4 squared. That's a circle centered at the point 2, negative 3, with a radius equal to 4. So there's the center of the circle. And that's what it looks like. So we should be able to go from the equation to the graph, from the graph to the equation. And then additionally, if I had x squared plus 2x plus y squared plus 4y equals 10, I should be able to convert this equation, x squared and y squared, into the vertex formula for graphing that circle. Very similar to the way we did with the parabola. All of this modeling is really one of the biggest ideas in mathematics. Really given a set of data, graph that set of data. Once you graph that set of data, identify what relationship it has, know the parent graph of it, and then find a specific equation of that graph. And then the whole point of all of that is so you can build a model and make predictions. Number 13, using substitution to solve. This is just solving algebraic equations that are kind of hard to figure out. This thing looks really ugly and complicated, so I'm going to solve this with substitution. This thing repeats itself, so I'm going to take that complex thing and set it equal to u. So I'm going to say u is equal to the square root of 2x plus 1. Now that I have that substitution, I substitute that out with the u. So I have u plus 3 over u is equal to 4. A couple ways to solve this. Either the fractions, I get a common denominator. If I want to do that, to add them together, I would multiply this by u over u, 1. And then now I could add these two fractions together, give me u squared plus 3 over the common denominator of u. Cross multiply, both sides multiplied by u. I have u squared plus 3 equals 4u, it's quadratic. U squared minus 4u plus 3 is equal to 0. I could factor that into u minus 3, u minus 1. Right, so then now I have, let me double check that, u squared minus 3u minus 1u plus 3. So now I use the zero sum property, and either this equals 0 or this equals 0. So either u minus 3 equals 0, so then u is equal to 3, or u is equal to 1. I have two solutions for u, and I know u is equal to that. So then I have to take my substitution and set it equal to u. So either 3 is equal to square root of 2x plus 1, or 1 is equal to square root of 2x plus 1. Solving for x here, I square both sides, and I get 9 is equal to 2x plus 1. Subtract 1, 2x is equal to 8, x is equal to 4. Or here, I square both sides and get 1 is equal to 2x plus 1. Subtract 1 from both sides, 2x is equal to 0, x is equal to 0. So I have two solutions. X equals 0 or x equals 4. Solving with substitution, I know it's kind of a hard one to see. Number 14 is nonlinear systems. And that, if you have two different nonlinear systems, like say y equals x squared, like a parabola, and another linear function y equals 2x plus 4. I could solve that systems of nonlinear equations like I would linear systems. Take that value for y, plug it in for y, giving me a quadratic, 2x plus 4 equals x squared. Set that quadratic equal to 0, and then solve that quadratic. Number 15, graphing nonlinear systems. So be able to graph that linear function, or that parabola, or that cubic, or whatever it is. So that brings us, I think, of our top 20 ideas for our midterm, up to 15. So that's 1 through 15. Okay, moving right along. Number 16 is solving one variable inequalities. A lot of these are absolute value or squared. So let's say we have the absolute value is 6 minus 3x plus 12 is less than or equal to 15. So first thing I'll do is subtract 12 from both sides. 6 minus 3x less than or equal to 3. And then with this, I'm going to just treat it like an equation first. And I know inside that absolute value it could either be 3 or it could be negative 3, because then I take the absolute value to get 3. So I have 6 minus 3x is equal to 3, or 6 minus 3x is equal to negative 3. Subtract 6 from both sides. Negative 3x equals negative 3. Divide by negative 3. X is equal to 1. Or over here, negative 3x is equal to negative 9. Dividing by negative 3, x is equal to 3. So there are two solutions. I treat it like a equality, but it's an inequality. So now I draw it on the number line. These are my critical points at 1 and at 3. It's equal to, so it's a closed dot and a closed dot. Then I have to figure out where it goes, if it's between the 2 points or if it goes out. So I just pick a value like here, say like 2. I take that 2 and I plug it in here. So I take 2 and plug it in there. 6 minus 6 is 0. 0 plus 12 less than or equal to 15. 12 is less than 15, so that holds true. So that point is inside those 2 points. I could do another check, like I'll try 0 here. This point, 0. I'll take 0 and plug it in here. 6 minus 0 is 6. 6, absolute value 6 plus 12, 18. Is 18 less than or equal to 15? It is not. That is not in my solution set. And I could pick another value out here. So that is 16, solving one variable inequalities. Number 17 is given is piecewise graphs. So let's say I have a linear function and it's a parabola right there. And this point right here is 3. This is 4, and this crosses at 2. First thing I want to do is just break this into pieces. So this is a linear function. Here, I can do 2 colors here. This is a linear function. Y equals mx plus b. The idea is the ideas are always the same. Given a picture, come up with an equation. And the changes is we're going to add domains and range to them or parts of them. But it's really the same idea again and again. So from that general equation, I go specific. Y equals mx plus b. It has a y-intercept of 2. From 2, it rises 2 and runs 3. So it's y equals 2/3 x plus 2. I don't want all values of that linear function. I only want values of x less than or equal to 3. It's equal because it's a closed-in circle. And let's say this pencil thing here is a parabola. I'd find the equation of a parabola. Y equals a, x minus h, quantity squared, plus k. I'd have to have a point on here, like where it crosses. Here I take that point and I plug it in and solve for a, like we did earlier. And if this graph were cut off right here, I would say for values of x greater than or equal to 3. So that's a piecewise graph. I know I ran through that pretty quickly. And then number 18 is given the equations like y is equal to 3x minus 5 quantity cubed plus 10 for values of x greater than or equal to 0. And another graph, y is equal to a x minus 4 plus 3 for values of x less than or equal to 0, how you would graph both of those. So that's the reverse process of that. That brings us through 18. Number 19 is solving with the same base.
So if I get the bases equal, then the exponents have to be equal. So it's really more exponents. 8 is 2 to the third to the power of x plus 1. 16 is 2 to the fourth in the denominator. So I'm going to make it 2 to the negative fourth to the power of 2x minus 1. I distribute through there, so I have 2 to the power of 3x plus 3 is equal to 2 to the negative 8x plus 4. My bases are equal, so my exponents have to be equal. So 3x plus 3 has to equal negative 8x plus 4. I solve for x. Okay, and that brings us to our 20th ELO, or the top 20 idea, and that's finding the inverse of a function. So if I have f of x is equal to 3x plus 5, that's really the same thing as y is equal to 3x plus 5. The way I find an inverse function is I switch my x's and y's and solve. So I have x equals 3y plus 5. Solving for y, subtract 5 from both sides. Divide both sides by 3. And I have y is equal to 1/3 x minus 5/3. And the notation for function is f of x. Notation for inverse function is inverse function of x. So in this case, it would be equal to 1/3 x minus 5/3. So that's the top 20 essential learning outcomes, or the top 20 big ideas for Algebra 2 or Integrated 3. Hopefully that helps give you an overview of the biggest part of this class. Thanks for watching. If you liked the video, hit like or write your comments below. I'd love to hear what you have to say. Thank you.